I am Siobhan, and my background is in designing and analysing subsea cables. And today I'm joined by my boss, Caroline Lowry, the analysis manager, and Mike Wells, the sales manager for the renewable cables that we provide. And they're here to help me answer any really tricky questions that you guys come up with during this presentation. So the subsea cables that you may be more familiar with are those associated with communication. So this is a map showing you all the interconnections between different countries where we do have communication cables in place. And you can see the majority of them follow the old shipping routes, but there's a staggering amount of subsea cables that are in the sea today. And we're talking about in the region of 1.2 million kilometers as of the end of last year. So the newer versions are obviously made using fiber optics for data transfer. So when we're talking about communication, we're talking about when you talk to someone on the phone internationally, or when you're searching the internet. These are the fiber optic cables that are being used to bring you information and to send information. So in general, when we put fiber optics underwater, they're very, very delicate. So we will armor them using these sections here, and we will put on a protective sheath layer here as well, and to give them a bit of reinforcement, stiffness and protection overall. Now the other type of cables, subsea cables that we have, are cables to bring us energy from offshore wind sources. Now, you may not be aware of this, but in the UK, we have a huge amount of offshore wind resource. So in fact, we've got the majority of the installed capacity for offshore wind in the world. We're closely followed by Germany and China is heavily investing, so they may overtake us at some point, but as of now, we have the most installed capacity, which is awesome. And you can see here, so for each of the turbines you have on a wind farm, you'll need inter-array cables that connect each of the pieces of equipment to the offshore substation, and then you'll need a cable from the offshore substation, which is called an export cable, to bring it back to shore for us to use. So you're probably familiar with these graphs from the news or the Met Ocean reports that you're used to seeing. This is an example of where all the wind farms are around the UK as of today. So you can see that we're taking advantage of a lot of the wind that crosses across our coastline and strategically placing these wind farms accordingly. Now, in terms of the energy that we're actually generating from offshore wind already, it's about 10% of all energy, electrical energy generated by the UK. And that 10%, which is up here, equates to being able to power over 30% of the UK households. So it's a staggering amount of energy that we're producing already. And if you look at where we were back in 2012, just generating 7%, we've increased that over 4 times to where we are today, so in less than a decade. So it's really promising to see how much energy that we're actually collecting from a single source of renewables. And this graph here shows you that with renewable sources and nuclear energy, all the primary energy, we're actually more than 50% of the UK electrical energy is generated through renewables and nuclear, which is excellent. So we're getting closer to that target that Nick mentioned about the zero carbon emissions by 2050. Now, we've been able to do that by adding more wind farms, but we've also been developing the equipment and systems so that we can capture more of the wind energy and bring that back to shore. So that involved increasing the size and complexities of these turbines to where we are today, which is about 9 megawatts. Now, to give you an idea of the scale, I've put in a local reference. So we've got Newcastle Tyne Bridge. One of these turbines, their rotor blade distance is about the same size as the Tyne Bridge. And in terms of the height, we're looking about 3 times the height of Monument, which is pretty staggering when you think about it, considering a lot of these are offshore. Now, as the turbines increase and we're generating more power, we need our cables to carry even more power. So we need to increase our voltage ratings of our cables so that we can carry essentially the increased power. So in order to provide these cables, JDR are leading the way in the UK by manufacturing hundreds of kilometres of renewable cables. We supply them generally here in the UK and in Europe and also around the world. So you can see that we've got this state-of-the-art facility here. You can see this is the Hartlepool Headlands. I'm not sure how many of you were familiar with JDR, but we're not too far away from your doorsteps, those based in Tyneside. And it's really useful having the vessels come up here to the dock. This is our factory here, so you can see it's quite large. And that means that we can manufacture very, very long lengths of cable and load them directly onto vessels as they're easily transported to where they need to be. Now, in terms of what the cables actually look like, we've got two main designs. We've got these static designs. So these are, you've got this power core components, you've got your fiber optic cable here, and you've got protective armor wire layer here. Now these are static, so in general, the wind farms we've provided to have been closer to shore and coastal regions. So they are relatively short lengths, and we are able to have the wind turbine as a fixed structure in the seabed, and the connection point, or where the cable feeds into that wind turbine structure, is relatively close to the seabed. So the cable itself is relatively close and then sits on the seabed, which remains relatively static throughout its life. However, if you're in a scenario where you have a turbine with an cable entrance point that's a lot higher up, then what you'll find is you'll have a hanging length of cable down to the sea floor, and that hanging length is subjected to current and wave loading, which means that it will move quite a lot, and we will need to build in a bit more of a robust cable so that it can withstand that kind of fatigue motion that it's seeing, as well as providing us that energy. And that's why for dynamic cables you'll see a bit more armor, and it's contrahelically laid to give it a bit more torsional balance, and you'll have protective sheaths, so more abrasion protection with these as offered by these sheaths as well. In terms of size, we're talking about between 70 mil to about up to 120 or 200 mil, sorry. So that's about a range of just a bit bigger than a tennis ball up to about football or bowling ball size. So the size drastically varies, but the more we supply, the more we're seeing greater demands of power, and we're supplying cables in the larger ranges. Now, in terms of what goes into the conductor design, usually the conductors are stranded, and that gives the conductor a lot more flexibility rather than having a solid core. They're also made of copper or aluminium. Now, copper, as we know, highly conductive, which means that we can make the core quite small and still carry quite a lot of current. We've also got aluminium available. It's about roughly 60% as conductive, so we usually need slightly bigger cores if we're using aluminium as our conductor medium. Now, in terms of the insulation, okay, that's size based on the voltage that we're going to carry. So the majority of voltages, cables supplied at the moment are within the region of 33 kV, but we have developed cables that are capable of carrying up to 66 kilovolt voltage, and that's just shy of 300 times what you're getting out of your socket at home. So these are staggering quantities of energy that we're bringing back. And you'll have a metallic sheath as a basic component of your conductor, and that ensures that we have electrical stresses that are uniformly distributed radially around the conductor within the insulation, which is great. Okay, so in terms of transmission, when we're developing these larger and larger sizes of power cores, and when we're talking about large sizes at the actual core itself, if you look at most of the wires around your house or your lighting or your charger at home, they'll probably have a sort of 1.5 millimeter squared conductor inside them. Maybe 2.5 if you're looking at something that gives you a bit of power. The conductor sizes that we're talking about for flowing wind are up to 1,000 millimeters squared. So that puts a bit of perspective in how large we're talking. But as we increase the size of the conductor, what we see is we've got to account for the skin effect. So when we're applying when we have current flowing through a conductor, the resultant magnetic field forces the electrons towards the outside of the conductor, which increases the resistance and the inductance. And that's in a single core. So you can see there the current density is quite high around the edge of the conductor. And when you have two conductors in proximity to each other, you also have this effect where you have the change in the densities. Instead of going fully away round, they're affected, and you can see they're interacting with each other. So this is what we see in our press-oil cables, or our 3-core cables. You'll see the electrical density up here is quite high, and there's very little current traveling through this central section. So that's something to be aware of in terms of how we size the central conductors in each of the energy cables that we use. Okay. In terms of the insulation layer, which we know is sized in voltage, we need to make sure that we can minimize the electrical stress. So that's the volts per meter inside the cable. And it's highly dependent on geometry. So if we have a stranded conductor, conductor is this shape here. And if we extrude insulation straight over the top, what we end up with is this geometry change where the curvature is changing, and we get this massive peak of voltage. So that's what we want to avoid at all costs. We want a nice uniform set. So what we do is we put in this extra layer on either side of the insulation, and this layer is applied over the conductor, and you can see there, and it offers a very smooth surface for the insulation layer, which is here, to go on. So this layer and this layer is semiconducting, and we apply them in a triple extrusion operation. So what we could do is, if we had a power core, we could apply this in one operation, then in this in another operation, and then this in another operation, so stagger them out. However, we want the insulation layer is critical in a power core, so we want to ensure that there's minimal chance of any contamination getting into that 3 sections as possible. So what we do is we apply it through this triple extrusion method, which means that the 3 layers are applied in one operation, similarly to how toothpaste is produced. Okay. Right, now in terms of putting cables underwater, most of us will know that water permeates through plastic. It's an unfortunate fact, but it's one that we need to deal with. So we've got multiple different designs that we can offer, and that is known in industry. Now, what we could do is put some sort of metallic barrier, and that's what these 2 designs are about. So you might have a metallic corrugated layer over the core, or you might have a lead extruded jacket. Now, both of those are there to try and fully enclose the cable and prevent water from permeating through. However, they're very, very large, and they're quite stiff, as you can imagine. So we look at different ways where we can minimize or mitigate against water permeation through, and we'll play around with the layers that we apply. And the selection of the layers in a core is dependent on the situation it's going in. So we could put various sheathing arrangements instead, or combine it with some kind of foil arrangement. Now, when we're talking about foil, we're talking about foil that's extremely thin. So if you think of oven foil at home, it's that kind of thickness that we're applying to our cores. And what we'll do is we'll overlap that foil and we'll glue that section. So what we'll try and do is make the overlap incredibly large, and what that does is it makes it more difficult for the water, because it has to permeate all the way through this layer before it can get through here, and we can predict times of that. So that's the reason why we would vary designs. And a smaller design generally results in a more flexible conductor, which means we can provide a more flexible cable, which means it's easier to install and handle and transport. Okay, so we also need to worry about cable temperatures. So when we're using anything that it was drawing a high amount of power through it, obviously there's a propensity for that to heat up. So what we'll do, we can do it through computational modeling, but we'll also, if we've got a tricky scenario, we will look at doing some FEA modeling, especially if we've got some other heat source in the environment. And what we can do is we can put current through these conductors and predict how hot the outside of the cable is going to get, and predict how heat is distributing through this area, depending on, of course, the environmental temperature around it. If we get a collection of cables together, you may find that there is a heat that builds up because they don't have as much heat dissipation. And that's very similar to when you buy a very long extension cord, for example, like a caravan, and you need to you're going to use it to draw a lot of power through it, to power your caravan for a long period. Most of the manufacturers will say you need to uncoil or unravel that cable to ensure this kind of heating effect doesn't occur. And there have been several incidents where that hasn't taken place, and there have been incidents of fires. So that's something to be aware of when dealing with any kind of electrical cable, to manage the heat dissipation. Okay, now in terms of how we build the cables themselves, we want to twist up our conductors, and we're applying the twist so that the conductors form a sort of helical structure within the bundle. And the reason we do that is to try and equalize the tension and compression that is seen when we bend the cable in its entirety. So you can see here, if we bend it around quite a large OD, really, this section or this component would see a lot of compression, and this section would see a lot of tension. So we try and equalize that out so that the tension and compression is balanced out. And it means we can bend the cable to a much smaller diameter without having any issues with the components. So if you think about it, if you thought about a runner, two runners running next to each other, this guy has to run a lot further around this track than this guy. If we put them on this path, they both sort of share and probably both going to meet at this point at similar times if they run at similar speeds. Okay. How we actually apply that, we've got these massive machines in Hartlepool at our manufacturing site. So putting a big power cores on these massive drums, which are about 60 tons in terms of capability. And they rotate around their own axis. And this carousel rotates around this central section. So it's rather like planets rotating around the sun. So this rotation is happening so that we can put these components up through this die plate here and twist them into the bundle. We want to twist these sections to make sure that it's straight in this. After we've assembled the bundle, we'll apply armor, and you can see that is also helically wound onto the bundle. And we'll apply either sheathing or rovings, as you can see. In terms of installation, we've come a long way from what it used to look like. These guys, you can see, you've got a raft or a jimmy raft stuck together, and these guys are doing quite a good job of really trying to monitor the tension or manage the tension of this cable as they pass it over. Considering the technology at the time, that's pretty decent, but we've come a very, very long way since then. So not only can we map the seabed and monitor the cable as it's being laid, but the tension control is very different. So if we have a cable stored on this section here, we now have very controlled tension as we lay this cable out. And that matters so that we can balance how the cable is being laid over the surface and ensure that we don't damage our cables. Right, so in terms of developments as we're going forward, I mentioned that we had dynamic cables, and they were required when you had a gap between the seabed and the entrance to a floating structure, such as a wind turbine. As we progress in wind farm development, we're trying to harness energy that's a lot further out, because the wind speeds further out to sea are a lot greater, and we've got these gigantic turbines that we're now producing. So the floating structure is usually moored with these big anchor lines, and we have to attach our cables somewhere in here so that it can be connected to the grid. So in this position, as it's moored, the floating structure can move. So we need to be able to make sure that when it's in its furthest position from the cable touchdown point, which is here, the cable length is still enough that it has enough pliability to be able to flex with the loading and minimize fatigue within that section and minimize tension. However, when the floating structure moves back, we also need to make sure that we can manage the length that was needed as it's all bunching up now. So we apply these little buoyancy modules, and that gives us a bit of thrust. However, buoyancy modules lose a little bit of their buoyancy over the lifetime of the product, so we'll also model the buoyancy at the end of the life condition, which is 20 to 30 years. And we want to make sure that the cable is not going to hit or disrupt the seabed on this section. So it remains intact in both conditions, the start and end of life. So, and that's where we're going through with cables and the new exciting challenges that we're seeing at the moment.